All right, so what we're looking at today is this idea of projectile motion, and it can be pretty easy in the fact that we've already looked at the different equations dealing with this. And so we're going to be looking at horizontal motion, which is our first unit. And then we're also going to be looking at vertical motion, which was the free fall, which was the second unit. And so it's easy in the fact that we have these two that we're going to be looking at. We've already looked at them. What makes it a little difficult is trying to determine which equations to use. And so hopefully as we go through here, we can see exactly how to use our equations and when to use those equations. So the first line that we have up here, it says that you have a projectile is fired horizontally from the top of a building at 20 meters per second. A projectile, first of all, is something that is flying through the air. And so instead of it just being in free fall, just falling to the ground, it is going to be falling and moving at the same time. So it has both horizontal and vertical motion. A projectile is not something that's in contact with a surface. So if you have like a ball rolling across the ground, that's not a projectile because it doesn't have only free fall and horizontal motion. It's in contact with a surface, which would give it a normal force, which that does not make it a projectile. If you have something rolling down a ramp, if it's in contact with that ramp or a slide, that's not a projectile. Okay. If it leaves the ramp, right, if it flies off of that ramp, then it would be considered a projectile. But as long as it's in contact with some surface, it is not. It says that it's fired horizontally from the top of a building at 20 meters per second. Usually when we talk about projectiles, we'll talk about it being fired from the top of a building, a cliff, a mountain, something that's really high up off the ground. And so that's usually what we'll say. In this case, we have a building. And so what we're going to start off with is this, where it says, find the horizontal distance an object would go each second for 7 seconds. And what we're going to use is this equation here. Now that should look familiar to you. We've used this in the past. The difference is now we have the x, which is attached to it. We may have had that like that. I can't quite remember. But we have to be specific now because we have two different components that we're going to be looking at. We have the horizontal, but we also have the vertical. So when it says find the distance, the horizontal distance, we have to be specific that this is the equation that we're going to use for that. Okay, so we're going to practice some of that now right here in these boxes. And so we want to find what the horizontal distance would be each second for 7 seconds. I think I have an eighth one here. So this is what we're going to do. We're going to do this. We're going to say horizontal distance is equal to your horizontal velocity times time. So we're going to look for 1 second, the first second. So we want to know, what is the horizontal velocity? What would the horizontal velocity be? If you remember in this one this little sentence that we read initially, it said it was fired horizontally at this velocity, so the speed. So this we are going to plug in to our horizontal velocity. So that's what we're plugging in there. So when we do that, you should get 20. I'm not going to use units on there, just don't have the space to do that. And we want to know for each second. So for the first second, I'm going to plug in a 1, and I end up getting 20 meters. So what I'd like for you to do is to go in and start calculating on your own, what is the horizontal distance going to be at 2 seconds, at 3, at 4. And so go ahead and fill these boxes in. And then when you are finished, look up here and we'll see if what you got is the same as what I have up here. So go ahead and try that now. Practice this so that way you're used to seeing the formula, you're used to writing the formula, you're used to being able to plug in those things into that formula. So go ahead and do that at this time. It's a little repetitive, but the more you do it, the better you're going to get at it. We should be close to finishing up here. So whenever you finish, like I said, take a look up here and see if yours matches up with what I have. That last box, remember, we're not putting anything in that because I only wanted it for 7 seconds. It's not gonna, we could put something in there. It's not gonna pertain to, so it doesn't matter. So you should have for 1 second, 2 seconds, 3, 4, all the way up to 7 seconds. And what we're looking at is just trying to say if all we had was horizontal motion, right? If all we were talking about was an object that was moving horizontally, right, from left to right, how far would it go if it was going 20 meters per second? 1 second would be 20 meters. If you allow it to go for 2 seconds, it would be 40 and 60 and so on. We've practiced with this, we've seen that, so this just kind of helps us to refresh our memory on that. So now what we want to do is we want to go ahead and jump into the vertical part of this. Did anybody have any questions on that? Pretty straightforward. So we're going to look at the vertical part of this. What we're saying here is how far would an object go if it was only dealing with free fall, right? The first part was horizontal motion. Now we're saying only vertical. So notice we are looking for distance, but in this case, we have a y attached to it. That y tells us that it's along the y-axis. We're dealing with the vertical axis. And notice that our equation is different. You're looking for distance up here, but our equation was horizontal velocity times time. Here, we're looking for distance, but now our equation is gt squared over 2. We use this a lot when we were looking at free fall. So let's go ahead and do the same thing and say if we were just looking at how far an object would go if it was in free fall. And again, it's kind of repetitive, but like I said, it helps to remind us how to do that. And the other part about this is make sure that you can plug it in into the calculator if you're going to use the calculator. You don't necessarily need to use the calculator on this first one, right? When we do this first one, we have gt squared over 2. G, go ahead and use 10. The time is, the first second. And then the 2 is that constant that we're going to have. It's always going to be there. So you can do this one in your head. You could say 1 squared is 1. 1 times 10 is 10. Then divide by 2 and get 5. Now, on later ones, if you need to use a calculator, use it. That's fine. I don't have a problem with that. But you want to make sure that you're putting it in the calculator correctly. Because you could have all of your numbers be correct here, but if you don't know how to put it on the calculator, then you're going to get it wrong. So make sure you can do that on the calculator if you need to. So we'll do the next one here. We'll go all the way to 7 again, just like we did earlier. So go ahead and start putting those in. If you can do that, go ahead. If not, look up here at a couple of these examples and see if these are the same numbers that you're getting. You want to make sure that you're paying attention now. It may seem like it's easy, but it will get more difficult, especially when we start looking at doing some of these equations and trying to do some of these calculations. All right, so having a couple of examples up here. Try those last ones on your own. See if you can get those numbers. Plug them in on your calculator. Try that out first. And then I'll put what I have on mine, and then you can compare yours to mine. I want to see if you can try these out on your own. And then that way you know whether or not you're getting these right. Because if you're just copying what I have, it doesn't really do too much. Because sometimes you're not going to be necessarily given 1 or 2 or 3. You may be given something like 2.45 or 7.3 or something like that. So being able to plug that on the calculator is beneficial. So for 7 seconds, you should get numbers that look like this. And so we're only looking at vertical motion here. So here we only have horizontal motion. And then here we only have vertical motion. So we've done some calculations with that. Now let's go in and start using our graph paper to kind of give us an idea, a pictorial representation of what our calculations actually look like. So it says, starting at the starting point, graph these points along the horizontal in red. So we have a starting point, and what we're going to do is we're going to graph these points along this horizontal here. So if you have a pen or a marker, you can use that. If not, you can get one up here at the front, get a marker or a colored pencil. It doesn't have to be red. It can be like orange or pink or something like that. Just some color that you can use to go across the top. But if you want to share it. I find that the different colors allow it to stick in your head a little bit more when you're looking at the different components. So go ahead and grab one of those, and we'll start to graph these. In addition, get a blue and a green. So get a red, a blue, and a green at this time. A red, a blue, and a green. Like I said, you can get like orange or pink or something like that. It doesn't really matter. So starting from the starting point, we want to start putting the points down where the object would be if it was just the horizontal motion. So if you notice down here at the bottom, it says each square in the graph will be considered 10 meters. So that means going across each square, each line is worth 10 meters. So if the first one, right, this first box here is 20 meters, if it starts at 0, the first line would be 10. and then 20 would be right here. So here's the first one at 20 meters. You don't have to mark anything down other than just where that object would be. You don't have to say that it's 20. And then just start putting all of those on. Start marking or plotting all of your points for the horizontal. Right? So 10, should be a mark at 20. That's this one. And then this is 30. There should be a mark at 40. And so go ahead and start marking those on your paper. And so when you finish, you should have something that looks like that. This is just a pictorial representation of where the object would be if you allowed it to travel horizontally for 7 seconds, right? Each line represents 10, so it'd be 140 meters away. This is if it only acted horizontally. The next thing that we want to look at is saying, okay, we saw what would happen if we had an object fired at 20 meters per second, but it only acted horizontally, right? Like acting as if there was no gravity there. Now let's look at it from the other point where what if there's no horizontal motion and it's just gravity? What would that look like? So with your blue marker or pen or whatever you have, blue colored pencil, we're going to go in and do the same thing, but for the vertical part. Right here, we have 5 meters. So if each one of these lines is 10 meters, for the first one, we're going to go halfway for that 5 meter mark, and we're going to put a mark right there. That would be 5 meters. For the next one, we want 20 meters. So that would be 10, 20. And then we want 45. So that's 20, 30, 40. Halfway would be 5. So put another mark there. So just be careful as you're going through here that you mark these appropriately. It's a little bit more it's difficult than the one across the top, because all of those are even. These are not. So go through there, pay attention, take your time, and then look back up here when you are. And so whenever you're finished, you should have something that looks like this. And so what we have is a representation of purely horizontal motion of something that's traveling at 20 meters per second. And then we have purely vertical if we disregard any horizontal motion and only look at it from the vertical here. But when we start looking at projectile motion, at projectiles, they don't just have horizontal motion and they don't just have vertical motion. Instead, they have a combination of both at the same time. It's not only moving horizontally, but it's also moving down at the same time. So to get an idea of what the object would look like, the path that it would take, we have to do a combination of horizontal and vertical at the same time. So the place where those two positions will meet is going to show you the path here. So what I'm going to do is I'm going to find the vertical, I'm going to come across and see where the horizontal and vertical would come in contact. So my first dot, I'm going to use green for this. If you have a different color, that's fine. My first dot on the actual path of that projectile would look like this. I will go to the next one. So in 2 seconds, this is where it'd be if it just fell. In 2 seconds, this is where it'd be if it was horizontal motion only. And I'm going to see where do those two come together. And I'm going to put a point right where those two come together, because what I'm looking at is not only the object moving forward, but it's also falling at the same time. So you don't have it end up here. You don't have it end up here. It's a combination. That's why it has kind of like that curved path, kind of like it at an angle. And so you'll continue to do that for all of these here. So go ahead and start putting all of those points in. Just be careful when you go in over these. That's why I'm using a pencil to do this. You don't have to. And so at the end of this, it should look like this. After you've established where the actual path of the projectile would be, right? It looks like this. What you can also include on that is a smooth curved line that connects the points, not a jagged line. You don't want to connect the dots. You just want a smooth line that will connect all of these points here. And so I'm going to do that and show you what I mean here. So the actual path of a projectile would look something like this. It's not just the horizontal, and it's not just the vertical. It's that combination of the two. That's why we say it has vertical components and horizontal components, because it's doing both at the same time. This curved path is called something specifically. In math, when you're graphing, when you get a shape that looks like this, what do you call that? It starts with a P. A parabola. That is correct. So we get this parabolic shape. It's called parabolic motion. So the shape that any projectile takes is called a parabola, or has parabolic motion. So it has this curve-like shape. This is only half of one, though. You could have where something is launching an object up, it'll go up in the air, but then it'll curve back down again. So it could have a full parabolic motion or a full parabola. Here it's only half, because we're starting up high. We don't have to wait for the object to get up high and then come back down. We're already starting up high, and then it's coming back down this way. So the shape of any type of projectile motion, the shape it's going to make is a parabola, or it has parabolic motion. All right. Let's move on to the next thing. If I look at the horizontal points up here, What do you notice about those points? What do you notice about those? What do you notice about these here? They're all evenly distributed. They're all equal distant. They're all equal distant. You can see that, right? They're 2 apart each time. So we know that the distance, the horizontal distance, is the same. Well, how do we get that? Let's draw in our velocity vectors. So we've been talking about distance, right? How far it goes. Now let's draw in velocity vectors to kind of give us, again, a pictorial representation of what the velocity looks like at those particular points. So what I'm going to do is I'm going to start here at the starting point. Let me zoom in here. And I'm going to draw a velocity vector from the start to the next point over. So I have started at the starting point and I have ended at the next position. I'm going to label that V of X because that's going to be a velocity vector. Specifically, it's velocity along the horizontal, along the x-axis. I'm going to do that for the next one. I'm going to start at the actual path and I'm going to end at the next position. And again, I'm going to label that V of X. And so for all of these, I'm going to go ahead and put in my horizontal velocity and label it V of X. So that way you get in the habit of actually labeling it correctly. And then also you can see what you have. Right? When you see V of X, you say, oh, okay, that's horizontal velocity. And so you'll continue to do all the way down. And so when you finish, look up here and see if this is what you ended up with. You noticed that the distance was all the same up here, right? They're evenly distributed, which means they were equidistant apart. How do you get the distance to be the same each time? Don't you have to maintain the same velocity? You have to maintain that same velocity. What do you notice about the length of all these arrows? They're the same. So if those arrows are the same, the velocity is what? Let me be specific. Let me use a different color here. The horizontal, I'm going to abbreviate, horizontal velocity is what? If it's all the same, we call that, starts with a C, constant. So we're going to write that in there, constant. And you're going to be asked that. You're going to be asked that several different ways. Right? The way that you're asked, it'll say horizontal velocity changes, it doesn't change, stays the same, right? And we give it some choices. Or it'll say the initial horizontal velocity is blank that of the final horizontal velocity. And you would say the same because this arrow is the same as this arrow. And so if these arrows are the same, we know that it's maintaining that same velocity. It's constant all the way throughout. But remember, it's the horizontal velocity that's constant. That's how you get these distances to be the same. All right, let's do the same thing, but do it for the vertical now. So the first one is really hard. It gets pretty jumbled in there. But if you tried to put an arrow, just do your best. Teeny tiny one right there. You may or may not be able to. Just try. And I'm going to label that, instead of v of x, v of y, because it's along the x-axis, straight up and down, rather than left and right. So I go to the next point here, and I'm going to start at that point, and I'm going to draw an arrow down until it comes in contact with that line where it would be if it fell for another second. Again, I'm going to label that v of y. And so I will continue drawing my arrows, my velocity vectors, and then labeling them as well. And so what you get is something that looks like this, right? It's a little bit different than the horizontal. What do you notice that's different about the vertical component of velocity? What's that? Aren't they getting longer? You start with this teeny tiny little vector here, a little arrow here, and then they get longer and longer and longer until you get to this end. Well, down here at the bottom, if we see that they're getting longer, I know we run out of space here, but as long as we draw an arrow that's a little bit longer than that, you can do that if you want. You don't have to, but if you wanted to, you could draw it in there and make sure it's a little bit longer. And so that way you have that one in there. If you wanted to, you don't have to. But again, we're increasing the length of the arrow for the vertical velocity. So what are we saying about the vertical velocity? I'm going to abbreviate this. It's unbalanced. We can say that it's changing, right? Would you agree that this little arrow up here is changing, and each one is changing? It's becoming a longer and longer arrow, which means that it's a greater and greater magnitude, which means it's getting faster and faster. Why does it speed up? Why does the arrow get longer? It's been a long portion of last couple of weeks talking about it. Why does the object speed up? Why does it speed up? What's causing it to speed up as it falls? Gravity. Gravity is causing this to speed up. It causes it to accelerate. There's an acceleration due to gravity. So it's changing. What's changing? The vertical velocity changes. And you'll be asked about this one as well. It'll say the vertical velocity stays the same, it changes, speeds up, slows down, whatever it says. I don't know how they'll ask it, but it'll say vertical velocity is not going to be the same. You can see that it's changing as it falls. It changes because of acceleration due to gravity. We have acceleration. All right. Gravity is not affecting the horizontal velocity. The horizontal velocity is staying constant all the way throughout. What is changing is the vertical component of velocity. It's getting faster and faster as it falls in the vertical part of it, not the horizontal part of it. All right, let's look at this last little bit here. I'm going to say this first, write it out first, and then talk about it. The horizontal component of velocity and the vertical component of velocity are independent. They are independent. So that's another bit of another type of conceptual question that you'll be asked. It says that the v of x, which is horizontal velocity, and the v of y, which is the vertical velocity, are independent of each other, which means this vertical doesn't matter. It doesn't matter what the vertical velocity is. It will not change the horizontal velocity. And it doesn't matter what the horizontal velocity is. It's not going to change the vertical. So I can say that, and it really doesn't mean much. But let's look at some of the numbers and see how that affects, or if it affects anything here. All right, if I go back to these numbers up here, and I tried to determine what the horizontal distance was after 1 second. Why was it 20 meters? Why was the distance 20 meters here? Because what? Because the velocity was 20 meters per second. That's exactly right. May seem like it's a simple question, but that's exactly why the distance is 20 meters, because it was fired at 20 meters per second. So if you understand that, let's say that we change this 20, and let's say that we change it to 50 meters per second. If we change the initial horizontal velocity to 50 meters per second, what would the horizontal distance be after 1 second? It would be 50. And then 100, and then 150, and then 200. And so what that does is that makes these points spread out. That's called range, by the way. The range would increase. The range would increase. It would be further down range. What if instead of 20 or 50, what if we made this 100? What would the horizontal distance be after 1 second? 100, and then 200, and then 300, and 400, and 500, which would increase that range even more. We run out of space really, really quickly. What if I change this to 10? Then we would have 10, 20, 30, 40, 50, and so that would make the range smaller. So what is determining the range? What's determining how far those are away from each other? The velocity, the initial velocity is determining how far downrange those objects are going to be, those projectiles are going to be. A faster velocity or a higher velocity means you would have greater range. Less velocity means you would have less range. You wouldn't go as far. So let's use that same idea, and let's look at the vertical component now. At any, well, I'll go back to that in a second. For this one, let's say, it was 20 meters, but for this one, let's say we changed it to 50 again. Now, if I changed it from 20 to 50, what would this end up being right here, this first one? What would this end up being if I changed this to 50 instead of 20? What would this be? It would still be 5. What if you changed it instead of 20 or 50? What if we made it 100? What would this be? It would still be 5. Because where are we putting velocity in here? We're not. So it doesn't matter if this is 10, it doesn't matter if this is 20, it doesn't matter if this is 100. This stays 5. This initial velocity has no bearing on this. It will always fall 5 meters per second. What if the velocity is 0? It'll still fall 5 meters in that first second. This horizontal velocity does not matter with the vertical velocity. What does matter with vertical velocity? Gravity. Gravity is what's causing it to come down. is gravity affecting the horizontal up here? No, we don't have gravity anywhere in our equation. It's just the initial velocity. So these two velocities are not dependent upon each other. They're independent. One is not going to affect the other one. It's still going to go at its initial horizontal velocity. It's still going to fall at the same rate. If you took a bullet and you were to drop a bullet at the same height of a barrel of a gun, and you fired a bullet from the gun, dropped the bullet, which one would hit the ground first? The one that was dropped or the one that was fired from the gun? We just said it didn't matter. We just said it didn't matter. I know it's that same way all the time, but let me show you this this thing here. Show you this video here. It's really, really quick. It's from Mythbusters. I don't know if you would ever watch that.
What you got there? This is a good one. Picture two bullets, each exactly the same distance off the ground, each released at the exact same second, except one bullet is dropped to the ground, the other is fired from a gun. The classic physics thought experiment states that both bullets will hit the ground at the same time. Based on what theory? Based on the theory that the bullet that's fired from the gun has no wings on it, no lift. Thus, gravity has the same effect on it as it does on the drop bullet, and thus they hit the ground simultaneously.
Adam lays down a runway of white paper so the high-speed camera will clearly see and measure both bullets at the same time, in the same place, and in the same shot. All we need now in the drop zone is Janie's drop rig, so the boys can take a shot at physics history.
We'll hit it on the first shot. Really?
So the setup is where they are. It took a long time for them to do this. They have a gun right there. It's going to fire straight horizontal across. Way down at the other end, you can see kind of in the green, there's a thing that'll drop the bullet at the exact same time. And so they fire it and drop it at the same time. So the bullet is going to fall where the other bullet is falling. And you can see where that is right here.
You never make predictions. That's awesome.
Bullet drop versus fired. 3, 2, 1.
So the bullet came in, that's where it hit, and this is where the bullet was dropped. So it kind of goes fast, so I'll show it again. So which one hit first? They hit at the same time, right? It doesn't matter how fast the bullet is going. If they're dropped from the same level, that initial horizontal velocity is still going to fall at the same rate, just like the bullet that's falling. So if you're asked a question on any quizzes or tests or anything like that, it says which one is going to hit the ground first. They both are affected by gravity the same, and so they'll hit at the same time. And I think everybody every year thinks that the one that's coming out of the bullet is going to stay in the air longer, but it's still falling. Again, it's just going further, but still falling at that same rate. So, pretty crazy. Pretty crazy. All right, hold on to that.